In this example, we're asked to find the first three non-zero terms of a power series solution about x equals 0 to y prime plus 2x times y equals 0. So we want to find a power series solution about x equals 0. So we're going to write y as follows. It's sum from n equals 0 to infinity of a sub n times x minus 0 to the power n. So that's because we have x equals 0 here. Now on the final exam, I will ask you to find a power series solution about x equals 0, because that makes things a little bit easier. So we can actually simplify this as sum from n equals 0 to infinity of a sub n times x to the power n, or a naught plus a1 times x plus a2 times x squared plus etc. Now, we also need y prime, and we have a rule for that. We can find the derivative by finding the derivative of each of these terms here. And so the n moves to the front. So that's n times a sub n times x to the power n minus 1. And now the important thing is to realize that we start at 1, and then we still go to infinity. And the reason we start at 1 is because the derivative of a naught is 0. That's a constant. So if you write this out, you get a1 for n equals 1 plus 2a2x plus 3a3x squared plus etc. So that's our y prime. So let's plug that into our differential equation. So our differential equation is y prime plus 2xy equals 0. And so when we plug in y prime, we get the sum from n equals 1 to infinity of n times a sub n x to the power n minus 1. And then plus 2x times the power series for just y. So that's the sum from n equals 0 to infinity of a sub n x to the power n. And then that is equal to 0. Now we can simplify that a little bit by bringing that x into this summation and that 2. So from this, it follows that the summation from n equals 1 to infinity of n times a sub n x to the power n minus 1 plus, and then n equals 0, and then 2a sub n x to the power n plus 1. And we get that from the x to the power 1 times x to the power n gives you x to the power n plus 1, and that equals 0. Now, in order to figure out what our coefficients are, so what is a naught, what is a1, etc., we would like to combine these two power series. But what we should note here is that the power series do not agree. So here we have n minus 1, and here we have n minus 1, or n plus 1. So the powers do not agree. So we're going to write both of these in terms of k. So for the first one, we want to use k equals n minus 1. And so that's equivalent with n equals k plus 1. And for the second one, we want to use k equals n plus 1. And so n equals k minus 1 for that. So our power series now change as follows. So we have the sum to infinity. Instead of n equals 1, we have k plus 1 equals 1. And then instead of n here, we have k plus 1. And then instead of a sub n, we have a sub k plus 1. And then x to the power k. And for the second one, we get plus summation to infinity. And now it's, instead of n, we have k minus 1. We have k minus 1 equals 0. And then 2 times a sub k minus 1. And then x to the power k. And that equals 0. Okay, so what we see is that this summation starts at k equals 0. Right? Subtract 1 from both sides. So we can simplify this to k equals 0. And the other one starts at k equals 1. So let's get the term with k equals 0. Let's pull that outside. So if we plug in k equals 0 here, we get 0 plus 1 times a sub 0 plus 1 times x to the power 0. And then we have the sum from k equals 1. We took care of k equals 0 right here. So k equals 1 to infinity of k plus 1 times a sub k plus 1 times x to the power k. And then our second sum is k equals 1 to infinity of 2a k minus 1 x to the power k equals 0. Now, this has to hold for any x. And what we see here for that first term actually just simplifies to a1. And since this has to hold for all x's, we could, for instance, plug in x equals 0, and that would make these two series completely equal to 0. And so from this, it follows that a sub 1 equals 0. Okay, now let's compare these two, and we can combine these two now because they both have an x to the power k and they both start at the same point. So now I have the sum from k equals 1 to infinity of k plus 1 times a sub k plus 1, and then plus 2 times a sub k minus 1, and all of that times x to the power k equals 0. Now, if this holds, right, this summation holds for all x's in an interval, the positive interval of convergence, then these coefficients have to equal 0. So from this, it follows that k plus 1 times a k plus 1 plus 2ak minus 1 is equal to 0. And this holds for k greater than or equal to 1. So now we can solve that for a sub k plus 1. So what we get then is that a k sub k plus 1 is equal to negative 2 over k plus 1, and then times a sub k minus 1. So this gives us a so-called recursive relation between the coefficients, and we can use that to figure out what the different values are for our coefficients. So let's take a look at, for instance, what happens when we plug in k equals 1. So when k equals 1, we get a of 1 plus 1, so that's a2 equals negative 2 times, or negative 2 over 1 plus 1 times a sub 1 minus 1, so that's a naught. In other words, a2 is negative a naught. Now, we don't know what a naught is just yet, and in fact, we will not be able to determine a naught because that depends on an initial condition for our differential equation, which is not given. So for now, we'll just write down a2 is negative a naught. So what do we get when we plug in k equals 2? Then we get 2 plus 1 is a3 equals negative 2 over 2 plus 1 times, and then plug in 3 here, or plug in 2 here, gives us a 2 minus 1, so that's a1. So we have a3 equals negative 2 over 2 plus 3, and that tells us that A3 is equal to negative 2 over 3 times A1, but we know that A1 is 0, so that's 0 as well. So we know that A3 equals 0. So now we can do a couple more values. K equals 3. So K equals 3 will tell us what A4 is. So A4 equals, if we plug in 3 here, we get 2 over 3 plus 1. Negative 2 over 3 plus 1. So that's negative 1/2 times A2. And we know that A2 is negative A0, so we can actually say that A4 equals 1/2 A0. And then we could do one more. K equals 4 would tell us that A sub 5 equals negative 2 over 5 times A sub 3, but A sub 3 is 0, so that tells us that A sub 5 equals 0. And so what does our solution look like? Well, remember we started out with y equals summation from n equals 0 to infinity of a sub n x to the power n, which is a0 plus a1 times x plus a2 times x plus a2 times x squared plus a3 times x cubed plus a4 times x to the power 4 plus a5 times x to the power 5. So let's plug in what we know. A0, we cannot determine what that is because that depends on the initial condition. But then A1 is 0, so we get 0 times x. And then plus A2 was negative A0, so we can write negative A0 times x squared. And then A3 was 0 again, so we have plus 0 times x cubed. And then A4 was 1/2 A0. So we have plus 1/2 A0 times x to the power 4. And then plus 0 times x to the power 5. And what you'll see is that all the odd powers of x will just disappear. And our final solution, our final answer to this question looks as follows. So we then have y of x equals a0 and then minus a0 times x squared and then plus 1/2 times a0 times x to the power 4. And then you would continue that if you were asked to find more terms, but we were asked to find the first three non-zero terms. So these are our non-zero terms of the solution.